In this video, we will take a deeper look at covalent bonding. But remember, this is just a review. So we will briefly cover topics like atomic orbitals, valence bond theory, and molecular orbital theory. First, let's start with atomic orbitals. All of these ideas come from the field of science known as quantum mechanics or quantum chemistry. And this field treats electrons as wave-like properties, not just particles. We start from a simple system, a system of a hydrogen atom consisting of a single electron and a single proton. And from this simple system, we can write what is known as wave equations to describe the system's energy. And once these equations are solved, we get what is known as wave functions, represented by the Greek letter psi. The mathematics of this is beyond the scope of our discussion. What is important, however, is the conclusion it provides us. And there's two main takeaways from these wave functions. The first takeaway is that electrons exist at discrete energy levels. Another way to say discrete is quantized. This is why it's called quantum chemistry. The second takeaway is that the energy is a function of spatial location. From this, we can draw electron density maps, or the probability map of finding an electron at a certain spatial point. This map is called the atomic orbital. In this class, we will focus mainly on elements of carbon, nitrogen, oxygen, which is basically on the second row of the periodic table. So because of that, we will focus on only two types of orbitals, the s orbital and the p orbitals. The s orbital is a spherical density map. The p orbital is a density map that has a node in the middle. It's like a bow tie on its side. Remember that these shapes are telling us that there's a chance of finding an electron there. So therefore, a node is a region where there is no chance of finding an electron. Another note of interest is that there are phases in these orbitals. As highlighted in the p orbital, the top lobe and the bottom lobe are out of phase of each other. And we can signify this by shading in the lobes with a different color. I've done it so where the top is red and the bottom is blue. This is arbitrary. Furthermore, there are three p orbitals. One p orbital in the x-axis, one p orbital in the y-axis, and one p orbital in the z-axis. All of these p orbitals are equal in energy. To summarize this part, I want to reiterate that the atomic orbitals are basically these maps that tells us where we can likely find the electrons. Notice in the s orbital, you can find the electrons within that sphere. Whereas in the p orbitals, notice at the center, where the x, z, and y axis meet, right at the center, that's the nucleus of the atom, right? So electrons in the p orbital can never be found at the center. That's at the node. But you can find them if you radiate out from the x, y, and z directions. So again, in this class, we will only focus on the 1s, the 2s, and the 2p orbitals. Remember that the number in front tells you the energy level. The lower the number, the lower the energy level. And it is associated with the row of the periodic table. And then the letters following that tells you the shape of that orbital. So let's map these orbitals relative to their energy. First, we have the 1s orbital, followed by the 2s orbital, then the 2p orbitals. Remember, there were 3 p orbitals, and they are all equal in energy to each other. So for hydrogen with only one electron, we can see that its one electron resides in the 1s orbital. We can signify one electron with one single arrow. Now remember, technically, these orbitals were solved for the simple case of the hydrogen atom. We can, however, extrapolate and apply it to all other atoms, simply knowing how many electrons it has. For example, we can try with lithium. Knowing that each orbitals can accommodate 2 electrons, we can fill in this diagram from the bottom up. Lithium with its 3 electrons start out with having 2 electrons in the 1s orbital. We've drawn it 1 spin up and 1 spin down, and its last electron in a 2s orbital. Let's try this again for carbon. Carbon has 6 electrons. So how can we draw its electron configuration? 2 electrons in the 1s orbital, 2 more electrons in the 2s orbital. Because electrons like to be as farthest away from each other, we don't want to put them in the same orbital unless we have to. In this case, because the p orbitals are degenerate, we can sprinkle and spread out the electrons throughout each p orbital. So instead of having 2 electrons in one p orbital, we can have 1 electron in each p orbital, leaving 1 empty p orbital. Now that we can describe electrons existing in what we call atomic orbitals, we can take a deeper look at what is covalent bond. And one way to see it is through what is known as valence bond theory, which states that a bond is created when there is constructive interference of overlapping atomic orbitals, a sharing of electron density. Taking a look again at the hydrogen bond, we can see that each electron is in the 1s orbital. When they come closer to each other, and there's an overlap, it would create what is known as a sigma bond. Let's now apply this valence bond theory to a more complicated molecule, CH4, methane. Which orbitals are overlapping to create the bonds in CH4? Remember the energy diagram for carbon? Notice that there are only 2 electrons that are by themselves, so therefore it can only make 2 bonds. So then how can methane, the carbon in methane, make 4 bonds to 4 hydrogens? So what we can do then is we can excite one of the electrons in the 2s orbital and to promote it to the 2p orbital. Now we have 4 single electrons that can each individually overlap with the 1s electron from hydrogen, forming that 4 bonds. But remember that the 2p orbitals has directions in x, y, and z, and they're all orthogonal to each other, 90 degrees from each other, which doesn't mirror reality. So instead of this, what we need to do is to hybridize these orbitals. We take 1 2s orbital and 3 2p orbitals, mix them together. The word hybridize means to average out these orbitals. Because we are hybridizing the orbitals, it will be part 2s and part 2p character. Because there are 3 p orbitals that are contributing to the new hybridized orbital, it will resemble more of the p orbital. And since it's an average, the energy then will be closer to the p orbital. Since we took 4 total atomic orbitals, we get out 4 hybridized orbitals. And this hybridized orbital is called sp3, meaning it has 1 part s and 3 part p. And all of these orbitals are degenerate in energy. To complete this energy diagram, we also have that remaining unhybridized 1s orbital. So now that we have the sp3 hybridized orbital, we no longer have the constraint of the px, py, pz geometry. But now we'd rather have an orbital called sp3, which looks a little bit like a p orbital that's a little bit more bloated on one side. Now, if you combine 4 of these orbitals together, they will try to be as far away from each other as possible. Since there's 4 things, the geometry that it will take is actually something called tetrahedral. So if I drew in the sp3 orbitals for carbon, it would look like this. All right, so now we can then add in the hydrogen 1s orbital to draw in the valence bond theory for CH4. So in CH4, all of these overlaps are head-on. So what would we call these bonds? They're called sigma bond. Let's do this with another example, ethylene. Notice that in this molecule, carbon is bonded to 3 atoms. In the previous case of methane, CH4, carbon was bonded to 4 atoms. So instead of hybridizing all of the p orbitals and the 2s orbital, we only need to hybridize 2 of the 2p orbitals. Remember, we still have that 1s orbital that's unhybridized. And in this case, we also have the 2p, one of the 2p orbitals that's going to remain unhybridized. We will create 3 new hybridized orbitals from the 3 atomic orbitals. In this case, we took only 2p orbitals and 1s orbital. So this new hybridized orbital is called sp2. How would the sp2 orbitals be arranged spatially? Remember, since there are 3 orbitals that needs to be as farthest away from each other as possible, the shape it's going to have is trigonoplanar. So if we imagine this dot as a carbon, one of its sp2 orbital can be drawn like so, and the other 2 will be drawn coming out and away. If we take a look at from the top view, it would look like this, where they are separated with 120 degrees apart. So that's a top view for perspective, but we need to look at the side view in this case because there's that one p orbital left behind. Where would that go? So to be farthest away from the sp2 orbitals, it has to be orthogonal to those orbitals. So from that side view, it looks like that. If you want to draw the top view, it would just be going up towards you, and then the other one is just right below it. So that's the hybridized orbitals and the atomic orbital for one of the carbon. Let's draw it on the other side. Those are the sp2 hybridized orbitals and the leftover 2p orbital. So from this, we see there is one overlap already of the sp2 hybridized orbital from each carbon, giving us our sigma bond, our carbon-carbon sigma bond. There can also be a side-to-side overlap in the p orbital from the top and the bottom lobes. This overlap is not as prominent, therefore this bond is not as strong. It is known as a pi bond. So in this molecule, you have 2 bonds between the carbon-carbon atom. One is a sigma bond from the hybridized sp2 overlap, and the other is a pi bond from the leftover unhybridized 2p orbitals. To complete the picture, we can also draw in the carbon-hydrogen bond. There we go. We can also do this for a triple bond. Take a look at this molecule. So notice in this molecule, the carbon needs to only be bonded to 2 atoms, the hydrogen on one side and the carbon on the other side. So we need to only hybridize 2 of the orbitals, the 2s orbital and 1 2p orbital. This time we only generate 2 sp hybridized orbitals because we only took out 2 atomic orbitals. And we also have now remaining 2 2p orbitals. So how do the sp orbitals orient themselves? Because there's only 2 of them, the best way to be farthest apart from each other is 180 degrees apart in a linear fashion. So if this is my carbon center, the 2 sp orbitals will be 180 degrees from each other. So what's left over is one of the p orbital. Again, we want to be orthogonal to be farthest away. So we can draw this as top and bottom. That's one of the 2p orbital. We still have another 2p orbital. It's now going to be in the z direction. Now let's draw it on the other carbon atom. Right? We have sp orbitals, one of the p orbitals, and then the other p orbital. Again, what do we notice that's overlapping in this case? The first one, easy to see, is there is a head-to-head overlap of the 2 sp hybridized orbitals, giving us a sigma bond. We also still see the p orbital overlap right there. That gives us 1 pi bond. And then we also see the p overlap on the z axis, giving us another pi bond. So in this case, we will have 1 sigma bond and 2 pi bonds. Again, to complete the image here, we can have the 1s orbital of the hydrogen with their sigma bonds. So in a nutshell, this is valence bond theory. In most cases, valence bond theory is enough for us to understand a system. However, it will fail us sometimes. In these instances, we must rely on what is known as molecular orbital theory. It is a more detailed and complex understanding of the covalent bond. Put in simple terms, molecular orbital theory, or MO theory, is using math to blend all the atomic orbitals within a certain molecule and spit out what is known as molecular orbitals. So we no longer have individual atomic orbitals from each atom that we use in valence bond theory. Now we have orbitals that represent the entire molecule. In fancy terms, That's known as linear combination of atomic orbitals, LCAO. So as an example, let's again take a look at the hydrogen-hydrogen bond. Remember that we said that each electron is in what is known as the 1s orbital. Now, if you were to blend these two atomic orbitals, combine them, you would have out what is known as molecular orbitals. Since we started out with two atomic orbitals, we will end up with two molecular orbitals. One known as the bonding molecular orbital, the other as the anti-bonding molecular orbital. The anti-bonding orbital is higher in energy because it has a node. So again, since we start out with two electrons, we will also fill out these molecular orbitals with these two electrons. The first two electrons will be in the bonding orbital. Since there are no electrons in the anti-bonding orbital, overall this molecule will have a sigma bond. Some more terminologies here. This is called the HOMO, which stands for highest occupied molecular orbital, and this is called the LUMO, or lowest unoccupied molecular orbital. Let's take a look at another example in the ethylene example here. In this case, let's just now focus on the p orbitals. So in this case, we have here the p orbital of the carbon and the p orbital of the other carbon. Individual atomic orbitals, we mix and combine them, they will give us two more molecular orbitals, the bonding orbital and the anti-bonding orbital. Notice that the bonding orbital has lobes that are shaded in phase to each other, whereas anti-bonding orbitals have lobes that are opposite of shades. Again, this orbital is higher because of that node. Filling in the electrons, again, we have the individual electrons from the 2p orbital from the carbon and the other 2p orbital of the other carbon. So a total of 2 electrons. So we will have 2 electrons filled up with the bonding orbital. We will come back to molecular orbitals and talk about them in more detail when they are of importance. For now, let's just have this level of understanding.